So now we know how to calculate the number of molecules that have a given chain length at any stage of the reaction given by the extent of reaction parameter P. So you can see that we're going to have a distribution of populations of different chains that have different lengths at any given time in the reaction. We can use that information to calculate things like molecular weight averages. So in particular, remember that the number average molecular weight is equal to the sum over the distribution of the number of molecules that have a molecular weight of a given value times that molecular weight divided by the total number of molecules in the sample. So I can break out this ratio Ni over N total and express that as one term and multiplied by the molecular weight associated with the chain length I. And in doing that, notice that I know what this Ni term is. We just determined what it is. It's this quantity, so I can put that in the numerator. And then the total number of molecules. So remember, we can get this by counting the total number of molecules that have unreacted functional groups, because that's the total number of molecules that are left at a given time in the sample. So I have expressions for this part of the equation, and that's multiplied by then the molecular weight associated with a chain of a given length. So I'm going to express that as the chain length I times the molecular weight of the monomer. Okay, so now I think you can notice that I have two kinds of terms here. And this prefactor associated with the number of molecules that are imers divided by the total number, that cancels out. And I'm left with the following equation to calculate the number average molecular weight. So I just need to come up with some expression that can help me to evaluate the summation, because I don't know what my distribution function is, so I can't, unless I know how many are present at each of these fractions, then I can't do the summation. So ideally, I'd like to re-express the summation in a simpler form that can allow me to actually calculate a result. So now let's take a look at this summation term and get an idea about how we can do this. So this is a bit of an aside, but it's just math. It's just counting and recognizing the behavior of these series summations that are present in this equation. So first, I want to back up a little bit and talk about a different sum. So imagine we talk about this sum, the sum of p raised to the I power over this population. So if I'm going to call that A just for shorthand. But so if I expand this out, sum of p to the I, that's going to give me p plus p squared plus p cubed all the way to n if I goes from 1 to n. Now, notice what happens if I multiply both sides by p. On the left-hand side, I have p times A, which A, again, represents what the total value of the summation is. And on the right-hand side, then I have p squared plus p cubed plus p to the fourth, all the way up to p to the n plus 1. So now I'm going to do a little trick. I'm going to subtract, I'm going to take equation 1 here, and subtract equation 2. So when I do that, on the left-hand side, I get 1 minus p times A, and then I get p, there's no other p here, so I have a p squared here minus p squared here. I have a p cubed here minus a p cubed here, all the way up to, I don't have an n plus 1 here, so I have 0 minus n plus 1. So the only terms that are left are the first term and the last term. So if I divide by then this term on the left-hand side, I get that this summation I can express only in terms of p, as follows: p minus p to the n plus 1 over 1 minus p. Then I can also recognize that for the kinds of problems that we're talking about, n is going to be big. In other words, the number of the molecular weights that are going to be in our population is going to go up to a large number, hundreds or thousands or more. So if that's the case, and p, remember, the magnitude of p is less than 1 because it's a percentage, a fraction of 1, probability that something happened. So for this case, then p to the n plus 1, so basically a number less than 1 raised to a large power, is going to give you a very small number. and it's going to approach essentially 0. So I can neglect this term with respect to P and express then this summation as the ratio of P over 1 minus P.